Welcome everyone to the presentation. My name is Geert Jansen. I'm a product manager with AWS, and I'll be talking about Amazon EFS performance best practices. I want to get us started with a couple of quotes. So the first quote might be familiar to many of you who've worked in software for a while. So all problems in computer science can be solved by another level of interaction. A quote by the famous computer scientist David Wheeler. There's a converse to this quote, and that relates to performance, which is any performance problem can be solved by removing a level of interaction. Having worked on performance for a couple of years now, I know this is very relevant, and if you've worked in performance, you might recognize this as well. Okay, so let's get started. So who's the session for and what will you get? There's sort of two audiences for this session. The first one is, you might be a DevOps practitioner, application owner, or a system admin, and you want to move an existing file-based application to EFS. So what you'll get out of this presentation is a basic understanding of your application's file system performance, as well as some best practices on how to configure your file system and your operating system. Second, you might be a developer that's developing a new application for EFS. And what you'll get out of this presentation is some specific considerations on how to develop a high-performance file-based application on EFS. Okay, so the agenda for today. First of all, I want to share spend a couple of minutes on how to think about performance. After that, we'll go to the EFS throughput and performance modes. We'll talk about operating system configuration and mount options. We'll talk about NFS caching and small file performance. We'll give some considerations for using directories. And finally, we'll end with a summary. Okay, so how to think about performance. So the way I think about performance is something that is quite similar to things like security and operational excellence. Performance has to sort of really permeate every component of your architecture in order to get the best performance to your end customers. And when I say it's a process, what I mean is, you need to make sure that each of your software developers, has the right tooling to measure the performance of their individual components. What you'll need is, some standardized testing, and what you'll need is running things like performance regression tests in your pipelines, just to make sure that everybody's, on the same page in your team with regards to performance. Everybody has the tooling and everything they need to make sure that each of the components, and as well as the system as a whole, has the right performance. Now, it's also very important to define goals for performance. Now, one goal might be, I just want to have the best performance possible. I would assert that that's not necessarily the best goal. Performance also has a cost associated with it. For example, you need time to optimize your application. That's developer time, that costs money. You might need additional servers or more powerful servers. So a better goal might be, for example, to have a goal that is related to something that your end users experience. So for example, if you have a web application, a good goal might be, I want my average page load times to be 50 milliseconds or less. Or say you have like a photo upload application or so, you could say, I want the upload performance for the P99 of my photos to be 2 seconds. After you've established a goal, it's pretty much an iterative process. So what you do is you'll measure your performance with regards to the goal that you've set, and you try to make changes and optimize your application and to improve performance this way. And then just repeat the process from that point onwards. Okay, and that's exactly the same what we do in EFS as well. So in 2020, we've announced a couple of performance improvements. One in April, where we announced a 5-fold increase in the read IOPS for general purpose mode file systems, as well as an additional announcement in July, where we increased the per client throughput by 100%. No, that's not all we've done. We've, in the background, been very busy, optimizing performance as well. And one particular area of focus, and we'll talk about this a lot more in this presentation, has been small file performance. Small file performance is often the bottleneck in applications, and that's why we made it a focus on addressing or improving that, in providing the best performance for Amazon EFS. So what you'll see here is a specific benchmark, git clone, which is a common benchmark used for measuring small file performance. And what it does, it basically clones the Linux kernel. And we've been running this benchmark over the last year. And what you can see here is our performance improvements over 2020. And so in the end, we achieved approximately 3x performance improvement over this on this benchmark. Okay, so let's talk a little bit about the performance and throughput modes of EFS. Starting with performance modes. EFS has two performance modes. General purpose mode, which is suitable for the large majority of workloads, and a max I/O performance mode, which is optimized for scale-out applications. The main benefit of the general purpose performance mode is that it has lower metadata and small file read and write latencies, while the max I/O performance mode has a higher number of IOPS. So GP mode can serve up to 35,000 IOPS, while the max I/O mode can serve in excess of 500,000 IOPS. So when we talk about metadata and small file performance, it is somewhat complicated to give like a representative benchmark for those. NFS has a dozens of operations, each with their own latency profiles. But what we found is there's actually two simple benchmarks we can give, which are easy to understand, easy to reproduce, and often correspond to a specific aspect of customer applications. And those are single-threaded file reads and single-threaded file writes. So on the reads, what we did is we wrote a simple benchmark. It reads 32 kilobyte files as fast as it can. And then on general purpose mode, this benchmark achieves approximately between 260 and 450 files per second. 260 is in the case where you first run the benchmark and everything is not cached. And then the second time, the 450 corresponds to when there is the data for those files would be cached by the local operating system. On max I/O, the same benchmarks gives between 80 and 160 files per second. On the right side, the benchmark is creating 32 kilobyte files, and on general purpose, you can create about 90 files per second, again, using a single-threaded application, while max I/O can deliver approximately 20 files per second. Okay, let's then switch to throughput mode. So the throughput mode is something that you can set when you create your file system, and you can change anytime thereafter. The default mode is the burst rate. Now, in the burst mode. In the burst mode, your file system can burst up to 100 megabyte per second per terabyte of storage. So the throughput you can achieve is proportional to the file system size, with a minimum of 100 megabytes per second. Now, if your file system does not have any more burst credits, what will happen is you will fall back to the base rate, which is half of the burst rate at 50 megabytes per second per terabyte of storage, with a minimum of 1 megabyte. So just as an example, say your file system is 5 terabyte in size, you would be able to burst up to 500 megabytes per second. Now, there are certain classes of applications that have higher throughput requirements, but have a low amount of storage. And for those, we introduced the second performance mode, which is called the provisioned throughput. Throughput mode, which is called provisioned throughput. With provisioned throughput, you can basically configure a fixed amount of throughput that is independent of the file system size. And that looks like this. Now, one interesting property of the provisioned throughput mode is that my apologies, is that you only pay for the excess throughput over the base rate of your file system. So for example, say you have a 6 terabyte file system, it would mean that the base rate for that file system would be 300 megabytes, 6 times 50, so 300 megabytes per second. If you would provision 500 megabytes per second of throughput, you would only pay for the excess of 200 megabytes per second. And when your file system grows, and at some point your base rate becomes equal to your provisioned rate, then you stop paying for provisioned throughput, and your file system falls back to the bursting rate. It can actually use the bursting rate and burst to higher levels of throughput. Okay, so Let's now move to the client side and talk about the operating system configuration and mount options. Okay, the most important recommendation that I can give here is to use a recent version of the operating system. When you use EFS, and EFS being an NFS-based file system, you'll access EFS using the NFS client that is bundled inside the Linux operating system that you're using. And that client is developed in the open source community and is continuously seeing a large number of improvements with regards to performance, features, availability. So by using a recent version, you can just basically effectively get more performance for free because you can make use of all these optimizations. So what is a good version of the OS? Now, good versions are, for example, Amazon Linux 1, RHEL 7.3, Ubuntu 16.04, and similar distributions that were sort of released at the same time. Better versions would be to use the very latest versions of these, so Amazon Linux 2, RHEL 8, or Ubuntu 18.4. Right, some of these operating system distributions provide kernel updates, or actually they all provide kernel updates, but some do it by giving a new version of the kernel. Others, take fixes and improvements from the upstream and backport those to the version they're shipping. But the point is that there will be updates even within those major versions, and so always make sure you use the latest kernel for the best performance. Okay, and just to illustrate that point, what I've done here is I used a particular benchmark, in this case a parallel small file read. So it's large number of small files, and the benchmark uses multiple threads to read as many of those as it can. And then I plotted the performance of that for different operating system versions. So RHEL 6, which was an older version released in 2010, has about a performance of about 300 files per second. RHEL 7, which was launched in 2014, has already over 8,000 files per second on this benchmark, while RHEL 8, which was launched in 2019, can support over 12,000 files per second on this benchmark. Okay, moving on then to mount options. It's important to use the recommended mount options for the best performance. The easiest way to do that is to install the EFS utils package. This package will install what we call a mount helper, which allows you to mount your file system with type EFS. So what this does in the background, it will set up a regular NFS mount, but it supports some additional features. So for example, it supports encryption in transit. It will also support authentication of the mount using IAM. But from a performance perspective, what it does, it will make sure that you have the best mount options available. And so the two that I particularly want to call out here are the NFS version, so using NFS 4.1 instead of 4.0. And the second is to use a read and write size of 1 megabyte. Now these are actually the defaults for recent versions of the operating system, but in older versions they were not. So if you use the mount helper, irrespective, you will get the optimized mount options. And then briefly here, the impact of using different mount options. So the top graph shows the difference between NFS 4.0 and 4.1. You can see NFS 4.0 achieves something like 300 files per second, again on the same parallel small file read benchmark as I used before, while NFS 4.1 achieves an excess of 12,000. For read and write size, I used a different benchmark to illustrate the difference. So I used a benchmark that writes to a new file as fast as possible, and then ran that benchmark for different sizes of the read and write size. So at 32 kilobytes, we're getting about 100 megabyte per second of throughput writing to that file, while at 1 megabyte, we're getting in excess of 350 megabytes per second writing to that same file. Okay, what we'll do here is to sort of explain how NFS caching and small file performance relates. In my experience, talking to customers, if there is a performance issue, most often it is related to small file performance. That's what makes this an important topic. And so let's dive into that. Quick overview of NFS. NFS network file system. So as the name implies, there's a client and a server. The client will be your EC2 instance or potentially a computer running on premises over something like Direct Connect. And then the server will be EFS. It's a simple request response protocol. So the client might send a request to the server to open a file, and the server could then respond with OK. It has a couple of layers. Since version 4.0, NFS runs exclusively on TCP. Below that, we have the RPC layer, which defines the request and response formats. And then at the NFS layer, that's where the individual file operations are defined. Okay, so let's talk about file system caching as sort of a generic concept. So we know pretty much since the early days of Unix that caching is important to get good file system performance. And so on the left-hand side of the diagram, what you'll see is how this works for a regular local file system. So I've got a single instance A, two processes, and they want to use the file system. Now the way they do that is they use they call into the kernel running on that instance A. And process A, for example, might request the kernel to create a file, and then the kernel at some point will then update the file system and create the file on disk. Process B the same. Now on NFS, it's slightly more general. On NFS, because it is a shared file system, we can now have multiple instances using the same file system. So in the diagram here, I've got instance A and B. Process A runs on instance A, process B on instance B, and both can request their copy of the operating system to to make modifications to the file system. And the question then that arises here is, if when and if does process B get notified of changes that are being done by process A? Now on the local file system, that is easy, right? Because both go through the same operating system, and there's a single cache. So even if process A created a file and the kernel decided not to yet actually write that file to disk, but to keep it in its cache, process B can already access that file because it goes through the same OS and the same cache. So process A and B have the same view of the file system, and at the same time they can also fully leverage caching to improve performance. And that's not the case for NFS, right? The only way a change that is made by process A on instance A can be immediately seen on process B is to disable all forms of caching, which will be very bad for performance. So what NFS does, it tries to come up with a balanced approach where there is some amount of caching with some rules and some particular behaviors that govern how this cache is managed. And that we will see is sort of the key to understanding small file performance. Okay, so let's get to it. So there's two sort of different types of data that are cached in EFS. There's metadata, so things like file attributes or file names or file handles, and then data, which is just the payloads for reads and writes. So for metadata, NFS takes a timeout-based approach. So if you would read, for example, the attributes of a file using the stat system call, that data can be served from cache if it is available. That cache typically has a time to live, or entries in the cache have a time to live anywhere between, by default, 3 or 60 seconds. So getting data from the cache might mean that you get the latest data. It might also mean that you get data that is stale and was modified on another instance anywhere between like 3 and 60 seconds ago. Okay, metadata writes, they also use the cache, but they are synchronous. So changing the attributes of a file, for example, will do a synchronous call to the file system. So those attributes will be immediately updated. The results can be stored in the cache, and so a future stat call could take those cache results and get them directly from cache. Now for data, situation is different, and this is where NFS defines the so-called close-to-open semantics. And the easiest way to explain this is to look at what happens when a client opens a file or writes to a file called foo.txt. So on the application side, it will basically opening the file with the proper flags to create it, writing to the file, and then closing the file. Now at the NFS level, the way this maps is quite interesting. So the open will actually be a synchronous call to the file system, to NFS, to create that file. Writes can happen fully local. So once a file is open, the write system call will typically not flush back, or at least not immediately to the server, but will keep the local data in cache. So those are very, very fast, order of microseconds. And then when the close happens, the close will first flush any dirty data using the write system call, and after that we'll close the file. So what you think about it is, after you've opened a file, there's no more sort of consistency between an open file on client A and an open file on client B. But once you close the file, all data is flushed back and you get back your consistency. So in this diagram, client A writes a file, foo.txt. File B opens that file after client A has closed it, and therefore sees exactly the same data that was available or was written by client A. However, if client A would open this file again while client B has it open, at that point in time, any data that's written by client A and would not be immediately available by client B because it opened the file before client A opened that file. So there is then a period where both clients have this file open, where they might not see the same data in this file foo.txt. If you look at why the protocol designers designed this, they see this as a compromise between performance and consistency. So the idea was, like, say that I have an editor and I edit a file on one server. After I save the file, everything is flushed and closed, and then on a different computer, I could have a compiler that then compiles that, reads that file and compiles that file. And as long as you close and flush and save the file on client A, the compiler on client B, or any other application using that file would always have the latest data. Okay, so that's close to open. So that is sort of one of the key, actually the key reason why small file performance is the way it is on NFS. So tying the two things back together here, so caching and small file performance. So on local file systems, we've seen that open and close can be served from the file system cache, and typically they are memory-based operations, and therefore they're typically memory-based operations that take an order of 10 microseconds or so. And because of this, programmers typically do not think about open and close as being expensive operations. However, on NFS, the close to open semantics require that both the open as well as the close have a synchronous call to the server that's take an order of magnitude milliseconds. So therefore, when you're reading and writing small files, the two operations, the open and the close, they might actually be significant with respect to the writes. If you have large files, it's not so significant, because say that you have to write a gigabyte file, it might take a couple of seconds to write that gigabyte to the server. So the additional millisecond or a couple of milliseconds for the open and the close don't matter much. But if you have very small I/O, then it actually becomes significant. Now, this is indicated in the table here on the right. I just created a simple benchmark that tries to open as many files as possible for existing files and also for file creates. And you can see that on a local file system, you get approximately a performance of 100,000 or so order of magnitude files per second. It's a little bit lower on the create side, typically a little bit higher on the open existing side, but that's sort of the order of magnitude. While for NFS, it is in the order of magnitude of 100. Again, higher for reads. On EFS, it's a little bit lower, roughly 90 for creates, but that's the order of magnitude. So how do we optimize this then? So we know that open and close are expensive operations on NFS in general, and in EFS being an NFS solution, also on EFS. Now, a couple of recommendations that I've used with customers, and we'll go into detail on each of these. So number one, don't unnecessarily close files if you don't need to. Number two is to use parallelism to reduce the impact of round trip times. And number three is considering bundling reference data. So first one, don't unnecessarily close files. Oftentimes applications, because when they were written, the programmers didn't really think about open and close being expensive. So say that an application needs to open the same file multiple times. Now, this might be a configuration file, might be some kind of input file with parameters, or whatever file it is. The easiest way to do that is just to open the file when you need it, read the contents, and then close it. So when you do this on NFS, you get into the situation indicated on the left. So the open will be a call to the server. So is the first read as well as the close. The second open will again be a call to the server. Then there will be a read from cache, right? Because the first read will actually have cached the data. The open has then validated that the cache is still valid, so the read can proceed from cache, and then we have a close. Now, if we want to optimize this, one simple way to do it is just not close the file, keep it open, right? So you have the same open and read initially, which require a round trip, but then any subsequent reads can be served from cache in order of microseconds versus the millisecond it would take to actually do the open again. And then finally, you have a close. Now, this can be an effective approach to optimizing your application performance. One thing to keep in mind, there are some limits on the number of file descriptors that you can have open. So if you have many files, you could increase those limits, as mentioned here in the box. So there's a global limit, which can be set with syscontrol, and there's a per user limit, which uses the limits.conf file. Okay, second optimization is to use parallel opens and close. So on the left-hand side of the diagram, it's again a sequential open and close. First the open happens, the application waits until the file is opened, and then the close happens, and again a round trip. Now, if you need to read multiple files, a more efficient way to do this is to actually issue all the opens at the same time, so that you don't have to wait in that case for the open to finish. You just do them all at the same time. You can then read everything at the same time and close everything at the same time as well. So in that case, the time it takes for the round trips is actually amortized over multiple files, giving you effectively a lower latency. If you do ways to achieve this would be, for example, if you use a programming language, you would use threads or multiple processes, or modern applications, they might use asynchronous I/O. And on the, if you use shell programming, there is this program called xargs, which has the GNU version of which has a capital P argument, apologies, which can actually run multiple commands in parallel. And by stringing together xargs with the capital P, you also need the -n, and look into the man page what that does. But by stringing together xargs and commands like find, you can easily create parallel versions of very common management operations. So things like copying a directory in parallel, deleting a directory in parallel, renaming files in parallel. You can typically create a pretty simple shell script to do those using xargs minus capital P. Now the graph here in this chart shows you the impact of doing things in parallel. This is again our parallel 32K small file benchmark. And you can see that with one thread, and this is actually a creation benchmark, so with one thread we're getting about 90 files per second, scaling all the way up to more than 400 files for 8 threads. Okay, last optimization that I want to mention here is to bundle files. So there's a class of applications that use a lot of reference files. So one example would be, for example, some kind of Monte Carlo simulation that needs parameters as its input, and those might be stored in separate files. Now, if you open those files sequentially, you get your millisecond latency for each of them. But what you could do is, rather than reading those files from a directory, you could actually store those files in a zip file. You could then open a zip file with a single open. At that point, you could read all the files in the zip file using this read operation that don't require an individual open. And when you're done, you can close the file. So I wrote a program to sort of show or illustrate this, and the results of this are in the graph on the right. So I created a directory structure with, I believe, something like 3,000 files. And then I had one program that just reads those files from the directory structure. And the program is programmed so that it can read a certain percentage of those files. So I ran it all the way from 10% to reading 10% of the files to reading 100% of those files. So if those files are stored in a directory, the performance is actually constant. Right? So we're reading, in this case, a little bit over 200 because it's uncached files per second. And it doesn't really matter whether you read 10%, 20%, or 100%. The performance you get is sort of in the number of files per second is fixed. In the zip file case, at about 10%, you're getting the same performance. But then once you increase the number of files that you read, so you're starting reading more of those reference files in that zip file, you're getting a lot higher performance, up to almost like 10x performance. So part of this is explained by the fact that you don't need the individual open and closes. Another part is explained by the fact that when the kernel starts seeing that you're accessing a large part of that file, it will actually read ahead some additional data, and so some reads might actually not need a round trip at all because you'll find that the data is already cached. Now when I say zip file for this optimization, I actually literally mean a zip format. Zip is a very interesting format because it has a central directory that allows random access to individual files in the archive. So you can basically pull out a single file without having to uncompress the entire archive. That makes it ideal for this use case. Other archive formats, like for example the tar format, do not have that property. Okay, so last topic for today is some considerations for using directories. So directories obviously are used by many applications to sort of structure data. But how do directories perform, and how do they perform with different sizes? Now lookups are easy because a lookup, right, which means opening a file in a directory by giving its name. So I want to open foo.txt in a certain directory. It doesn't really matter how large that directory is. The time it takes to do that lookup is constant time, order magnitude milliseconds. However, the other operations on a directory, so listing a directory, adding a directory, and listing entries, adding entries, and deleting entries, the performance of these operations is a certain number of entries per second, as indicated in the table here. That does mean that once your directories grow larger and larger, they become less manageable, because it might take seconds or minutes, for example, to list the entire contents of the directories. For truly humongous directories with like hundreds of millions of files, it could potentially take hours or more to delete that directory, for example. Also, large directories have actually some particular bugs in it in most Linux versions today. So listing very large directories that are being concurrently modified, is sort of a well-known problem. And only recently there have been some changes in the Linux kernel to sort of address that. So hopefully those changes will be in Linux 5.11. But without those changes, which basically includes most operating systems today, these actually could hang. Listing these large directories could hang if that directory is being concurrently modified on another system. So this brings us to then our recommendation for optimizing directories. And the recommendation here is keep directory sizes reasonable. So as I mentioned, there's not a hard and fast limit. Lookups will always be efficient. It's just you want to make sure you can still continue to manage your directory. So I personally use like 10,000 as an interesting, or as a reasonable size, a reasonable maximum size for a directory. But you can make it a little bit larger, a little bit smaller, depending on your application. But that's sort of a reasonable size. If you have more files, the recommendation is to use nested subdirectories. And one common pattern, which has been in use, for a long time, also on decades ago, Unix file systems have been recommending this approach, which is to use prefix characters from your file name as subdirectories. So I have a file called deadbeef.bin. It might be in a 3-level nested directory, with the first being the first character of the file name, then the second, and then the third. This will cut down by a lot the number of files in your directories, and keeps and make sure that your files, that your directories continue to be manageable. Okay, so a summary of what we've learned today. Number 1 is select the correct performance and throughput modes for your workloads. Number 2 is use the most recent operating system possible. Use the default mount options. Number 4, improve small file performance by optimizing the open and the close using any of the 3 approaches that we suggested. So using parallelism, bundling files, and don't close files if you don't need to. And the 5th recommendation here is to keep directories below 10,000 items if possible. Okay, before closing, I want to show on this slide briefly some of the other EFS sessions that are being broadcast using this during this reInvent. And I want to thank you for your attention today.